Welcome back. I think we'll begin this next lesson with another example. Before we get back to the theorem, let's do our friend the Fibonacci sequence. So the recurrence, Fn equals Fn minus 1 plus Fn minus 2. I can't remember. These are not the exact initial conditions I used before with the rabbit example, but let's just go with it. It's what I have in my notes here. F0 is 0, F1 is 1. So that gets our recurrence started. So, if you'll recall from whenever you watched the first video, for me it was just a mere minutes ago, we want the characteristic equation. So, replace the sequence with exponentials. The subscript becomes a superscript, so r to the n equals r to the n minus 1. We'll stop doing it in this much detail after this example probably, but we get this polynomial equation. Then we divide out r to the n minus 2. That'll leave me with r squared equals r plus 1. Then get everything the same side. And now we have our characteristic equation in its standard form. But now we need to know what are its roots. What are the solutions to the characteristic equation? This one does not factor, as they normally do not factor. Well, sorry, that doesn't factor with nice whole numbers, with nice rational numbers. And in general, they do not factor nicely. So in this case, we need the quadratic formula. So the solutions are going to be r equals negative b, so b is negative 1, so positive 1, plus or minus the square root of b squared is 1 minus 4ac. A is 1, c is negative 1, so this will become plus 4 over 2a, which is 1. So r equals 1 plus or minus the square root of 5 over 2. So we've got our two solutions, one with plus and one with minus. Let me write them separately, actually. Okay, so these are our solutions to the characteristic equation. Let me erase the intermediate work. What this gives us then is the information that we need for our general solution to the recurrence. Fn will have the form alpha 1 times the first of our roots, doesn't matter which is first, but times one of our roots, so 1 plus square root 5 over 2 to the n, plus alpha 2 times our second root to the n. Alright, now I can erase my roots. Alright, so there's our general solution to the Fibonacci recurrence. But now with these specific starting values, we plug in the subscripts and set up our systems of equations. So when n is 0, we'll get the equation 0 equals, when the exponent is 0, we'll just get 1, so we'll get alpha 1 plus alpha 2. When n is 1, we will get alpha 1 times 1 plus root 5 over 2 plus alpha 2 times 1 minus root 5 over 2. Because if our exponents are 1, that's all we're left with. Okay, so depending on how much work I want to try to do on this whiteboard, I think I can leave that to you safely. We solve this for alpha 1 and alpha 2. So do subtract one of these to the other side and substitute. We come out with the solutions. Alpha 1, if I make sure I label things consistently, we should come out with alpha 1 equals 1 over square root 5, and alpha 2 equals the negative of that because of this. Okay, so if you believe that, and do double check that, these are old notes that I didn't check beforehand. That should be right. That gives us our formula for Fn. Well, let me see me write everything. We get our formula for the Fibonacci sequence. Here. Right? So this just illustrates that clearly, and if we go through the Fibonacci sequence, F2, we're always adding the two previous ones. So F2 is 1, F3 would be 2, F4 would be 1 plus 2 is 3, and so on. F5 would be 2 plus 3 is 5, F6 would be 8, and so on. That's our Fibonacci sequence. It's clear from our pattern that we're never going to leave the realm of whole numbers. We always get whole number values. But that doesn't mean the formula will involve only whole numbers. Our roots are irrational here. But combined, this formula always gives us these whole numbers. Now, if I pick different starting values, if I pick irrational or whatever for initial values, then I will get non-whole numbers, clearly. But just to show you this for a non-simplistic example. All right, so next we want to go back and address the other case. So this is back to our theorem. So we had, let me try to be consistent with my labels here. Star was the recurrence. That's all it was. And then double star was the characteristic equation, which, let me just jump ahead. That was r squared minus c1r minus c2 equals 0. This was our setup. This was our data given to us. And we're trying to find the general solution. Our first case that we covered in the previous lesson was if this characteristic equation has two different solutions, then we know how to form we know how to form the general solution. So the second case is we have one solution, but it has multiplicity 2. So this case is going to be if R0 is a root of double star with multiplicity 2, then let's just state it like this. The general solution to star is AN equals, well, it's like we have two roots. It's just since multiplicity 2 that both of them are the same. So what I want to do the same idea. I want alpha 1 times r0 to the n plus alpha 2 times r0. I'm going to leave a space here. But alpha 2 times r0 to the n. So it's like I have the same root twice. But if I wrote this, I could combine, these are like terms. So I could combine alpha 1 and alpha 2 and just get a single alpha times r0 to the n. And that would kind of simplify my solution. But that's bad news because I don't have it written here, but these recurrences don't exist in a vacuum. They come with initial values, and if I've got a degree 2 recurrence, I'm going to need to have two initial values, like an A0 and an A1, for example. And if I have two different possible initial values, I need to have two separate alphas to work with. I have to be able to adjust two of them to get both those initial values to be correct. So if these are like terms and I can simplify it to just make it one alpha, I don't have enough freedom in my general solution to account for all possible general solutions. So what I need to do then is, for the second instance, I put in an extra n coefficient. Okay, so I don't want to prove this. There's a proof in the book that you can read, but this is the abridged version of these lectures, so I'm not going to prove that this actually works. But let's look at an example instead. If I've got one. Yes. All right. So. Oh, do we have our first guest lecturer? Come here. Wait me a second. All right, so my problem is an equals jump up there. All right, bye. She'll be back. 8 minus 1 minus 16 minus 2. Won't worry about initial conditions later. All right, so we've got this recurrence. So let's quickly do the characteristic equation. So it's always going to be, this turns into r to the degree, because when you divide that out, you'll be left with 2 here. So I'll have r squared, and then I'm going to subtract this stuff over, so I'll have minus 8 r to the first, and then plus, when I subtract this I get plus 16, and this won't have any r's. So there's our characteristic equation. This one does factor easily. This is r minus 4 squared. So r equals 4 with multiplicity 2. That's our only root, and it has multiplicity 2. So that tells us that our general solution would be an equals alpha 1 times 4 to the n plus alpha 2 n times another 4 to the n. If you like, and we'll say it like this later, but if you like, you could factor out 4 to the n and you'd have a linear polynomial, alpha 1 plus alpha 2n times 4 to the n. Let me write that down. So this is clearly the same thing. I just want to point to it and to think of it in a certain way. So when we have a repeated root 4, we have that exponential function, but then its coefficient is not a constant, it's a linear polynomial. So a degree 1 polynomial. It has two terms to it, a constant and then a degree 1 term. All right, so there's our general solution. You can check with a little bit more work this time because of the extra n. You can check though that this formula will satisfy this recurrence. I recommend trying to do that just to see these things work correctly, but check that maybe yourself. Then if we had some initial conditions, let's add those. So if we had this, and then we threw in the initial conditions, A0 equals 3 and A1 equals 10, then we first go through and find the general solution, which I have here. It's just not written in a good place. Let's do it like this. We plug in our initial conditions. When n is 0, I get the equation 3 equals alpha 1, alpha 2, n disappears because n is 0, 4 to the 0 is 1, so alpha 1 equals 3. And if I plug in n equals 1, I would get 10 equals alpha 1 plus alpha 2 times 1 times 4 to the first. So we know, well, we do this multiple ways, but we know alpha 1 is 3. So we got actually 10 equals 3 plus alpha 2 times 4. Sorry. 10 equals 12 plus 4 alpha 2. If I care enough, I'll erase my mistakes in the editing process, but all right, so that tells us what? Negative 2 equals 4 alpha 2. So negative 1/2 is our alpha 2. Yeah. So our actual solution for this recurrence with these initial conditions is an equals 3 plus negative 1/2 n, so minus n over 2 times 4 to the n. All right. Let's see. All right, so I think what I'll do next, well, let's make a couple observations. Okay, so let's address the higher degree homogeneous recurrences. So here's our general theorem. All right, so now we have a degree k. This is going to be very much the same theorem as the degree 2 theorem, but I'll just do it as one case. So we've got a recurrence, an equals c1 an minus 1, etc., down to ck an minus k. So then we convert this into its characteristic equation, and so that would be, won't go through it again, r to the k power minus c1 r to the k minus 1. Yeah. Basically, the n's become k's. Minus c2, etc. Minus ck. That won't have any r's with it. This will be equal to 0. So there's our characteristic equation if you go through the process. Okay. So this characteristic equation is a polynomial equation in the variable r. So we know from algebra that this is guaranteed to have k roots. So k r values that satisfy this equation. But some of them might be repeated as before with the degree 2. So I don't want to number these. R1, R2, up to RT be the distinct roots. Of this characteristic equation, double star. Okay, so this is a list of numbers. There are no repetitions in these numbers. So t has to be less than or equal to k. You can't have more roots than you have degree. But some of them might be repeated. And so let's address that here with multiplicities. Multiplicities, I would call these m's, m sub 1, m sub 2, up through m sub t, respectively. Meaning R1 has multiplicity M1, R2 has multiplicity M2, and so on. So most of these are probably 1, but some of them might be bigger numbers, bigger whole numbers. Then the general solution, you start to abbreviate that, to the recurrence is, okay, so this will look very intimidating, but just keep in mind our approach from the degree 2 case. AN will equal, what we want to do is add up exponents of each of these roots. And so if none of them were repeated, if no root was repeated, we'd have alpha 1 r1 to the n plus alpha 2 r2 to the n plus alpha 3 r3 to the n, etc. until we got to alpha k rk to the n. Right? But when there's repetition, so when you actually have multiplicities, then you have to throw in these n's to avoid like terms. But then, like on the previous example, with those multiplicities, you can then kind of combine all the parts with the same root, and you get these polynomial coefficients. So I'm going to write it like this: P1 of n R1 to the n plus P2 of n times R2 to the n, etc. until we get to P sub t of n RT to the n, where each Pi of n is a polynomial in the variable n of degree, it would be m sub I minus 1. So, like we saw with the degree 2 stuff, when the multiplicity was 2, the coefficient on the root to the n, the coefficient on the exponential thing, was a linear polynomial. Alpha 1 plus alpha 2 n. That's linear, which means degree 1 polynomial. So the multiplicity was 2. 2 minus 1 gives me degree 1. for that polynomial. Okay, so it's very, I mean, it's a simple enough concept, but it's hard to take in from the abstract here. So let's do an example. One or two examples here. All right, let me erase. I'm not going to worry about initial conditions for these. Let's just do the general solutions. All right. AN equals 5AN minus 2 plus 36AN minus 4. Yeah. Well, we'll go with this. Okay, so this one, it's a degree 4 recurrence. If we do the characteristic equation, this will be r to the 4th minus 5r squared minus 36 equals 0. Okay, so for these higher degree recurrences, these become basically factoring problems. And technically, I mean, we know that any polynomial can be factored down into its linear roots, linear factors. Some of those factors will involve complex numbers, as we'll see with this example. But any polynomial can theoretically be factored down to its linear factors. But in general, it's a difficult problem for random polynomials. This one, though, is set up to be doable. So out of this factor, this is first going to factor as r squared minus 9 times r squared plus 4 equals 0. R squared minus 9 factors is r plus 3 times r minus 3. R squared plus 4 is irreducible over the real numbers, but this does factor square root of negative 4. So negative 4, if r squared equals negative 4, you'd make this factor 0. So if r squared is negative 4, r needs to be 2i or minus 2i. So this is our fully factored characteristic polynomial. So our roots are r equals negative 3, positive 3, I did this backwards, but 2i and minus 2i. So one point I want to make with this example is, in general, some of our roots in these characteristic equations, some of the roots are going to be imaginary. That's okay. Just like with our Fibonacci example, where sometimes the roots are irrational, it still works. It's still the necessary component for our general solution formula. And so even though it's going to involve imaginary numbers, it'll give us a formula that gives us whole number or real number terms if our initial conditions are real numbers. Okay, so for this example, our general solution is going to be, in this case, none of these are repeated. We have 4 distinct roots. So the solution is going to be just a combination of the exponential expressions with these as the basis. So we're going to have an alpha 1 times negative 3 to the n plus an alpha 2 times 3 to the n plus an alpha 3 times 2i to the n plus an alpha 4 times minus 2i to the n. So there would be our formula for the general solution for this recurrence. If we wanted to find a particular solution, any choice of alphas will give us a particular solution. But if a more involved problem would be if I gave you some initial conditions, we could solve for particular values of these alphas. To get one unique solution, we would need to have 4 initial conditions. I would need to say what is alpha 0, what is alpha 1, what is alpha 2, and what is alpha 3. And so if you had all 4 of those, then we could get 4 equations with 4 unknowns, the alphas, and solve it. I'm not going to ask you to do one that involved. Okay, so this was simple. I mean, it was slightly harder factoring involved, but it's still a relatively simple example. I need to do one, though, that illustrates the more complicated multiplicity stuff. And that gets trickier to come up with examples. So let me just do it like this. I'm not going to tell you what the recurrence is. So suppose we have some recurrence, an equals something, and say we know the characteristic equation. So that we can already have it factored for us. Suppose the characteristic equation factors as r plus 3 times r minus 4 to the third power times r minus 8 squared equals 0. Erase that looks bad. So that was a 2. All right, so suppose we have some recurrence. We take its characteristic equation and then we manage to factor it completely and we get this. So that would be a long college algebra problem to factor that. I don't care about doing that. All right, but suppose we did all that work. Then our roots, and let's also do their multiplicities. Our roots would be r equals negative 3 with multiplicity 1, because that factor just occurs once. R equals 4 with multiplicity 3. R equals 8 with multiplicity 2. All right, so now we can construct our general solution. AN equals, we take the root, negative 3, we raise it to the nth power, and then the coefficient is going to be a polynomial of degree 1 less than the multiplicity. So if it just occurs, if the multiplicity is 1, that gives us a constant coefficient, say alpha 1. Let me avoid some ugliness with our subscripts and just use capital English letters for these. Let's call this a capital A for that coefficient. Then we move on to the 4. So we'll have 4 to the n as our exponential part. The coefficient to that, I didn't leave myself enough space. The coefficient of that should be a degree 2 polynomial. So 4 to the n, but in front of it, I need to have a degree 2 polynomial, 1 less than 3. So we need a b plus cn plus dn squared. Basically, this 4 to the n has to have 3 separate unknown constants to go with it. And they have to be separated by using different powers of n. So you start with a constant and you work your way up by introducing more and more n's until you have enough. I need 3 total, so I start with a constant with no n's, then I have a constant with an n, then I have another constant with an n squared. That means these are not like terms, so I can't combine them. I can't collapse them down to be a single constant. Okay? And then for 8, I'll have 8 to the n And in front of that, I need to have two separate terms. So we'll have what am I on? E plus F in. Right, so this is how you construct these. That's what the deal was with these polynomial, the P sub I of n stuff from the theorem. Okay, so if I wanted to get an exact solution, I would need, the degree here is 6. We've got 6 unknowns. My multiplicities add up to 6. So if I want to have a solution for an exact answer for each of these unknowns, I would need to have 6 initial conditions to go with my recurrence. I'm not going to be giving you problems of that level of complexity. All right, so I believe that basically covers the homogeneous recurrence, the linear homogeneous recurrences with constant coefficients. We know how to solve those, at least in theory. Solving those just amounts to a factoring problem. You write the characteristic equation, you factor it. We know it's theoretically possible to factor any of these equations. So you factor it to find the roots, and then you're able to construct the general solution. So this type of recurrence is now a completely solvable type of problem. Now our next topic will be the same thing, but with non-homogeneous situations. So we move from homogeneous recurrences to non-homogeneous recurrences, but they're still linear with constant coefficients. And so solving those is going to draw upon this stuff, but there'll be an added, I'll call it a step, but it's more complicated than that. But again, it's very similar to something you would have seen in differential equations. There you had linear differential equations with constant coefficients, and they came in non-homogeneous and homogeneous varieties. We'll basically be doing something that's analogous to, let me remember the terminology, undetermined coefficients, I believe. I don't know. I don't have my differential equations book with me, so I can't look that up. So I'm going to hold off and wait till the next video to start that. When I put these up, I will add some homework list, assigned problems from the book to help you practice with this stuff. I'll add it as a fancy kind of text overlay for the video. I can't remember if I already said this or not, but after I assign those problems, those are for your practice. Then eventually I will post what I'll call them quizzes. I'll post them to Blackboard, and I'll have the statistics tracking on so I can see who downloads them, but the grade for those will just be participation. So I'll check to see who downloaded it. If you did, you'll get full credit. I'll trust you to attempt to do the quizzes yourself, and then a few days later after that I will post an extra video of me going over the problems so that you can compare what I do to what you do and see how you did or see if I did it correctly. Right. So I'll stop it there and create more videos later.